I've got all these silly little slide transitions going on here. You can see, rather than putting up too much information on a slide at one time to break a slide, maybe little bits, and you can step through it like this, 3, 4 bits, because otherwise it's too much for you guys to take on. Unfortunately, when I put the slides up on the website, I left all those transitions in. So I think you had a big slide package with maybe 150 slides, when there's actually only about 40 unique slides. I've rectified that. I've put a new version of these slides up, which doesn't have the transition, so it's a much smaller package. If you wanted to print them out, for example, I don't know if you want to print them out. If you're doing it electronically, it doesn't matter either way. If you're printing them out, it's nice to not to have to print out 102. Okay, so last week we were looking at root finding, and we looked at the bisection algorithm, and the bisection algorithm is so simple, your granny could do it. It basically revolves around you somehow, and we didn't talk about how we would do this, but somehow finding an A and a B such that the root lies between them. Now, if you don't know what a root is, it's the whole purpose of root finding, how do you know that or the root is between A and B if you don't know where or is? Well, you know or is between A and B if the following condition holds: the product of f evaluated at A and f evaluated at B is negative. If that is the case, it means either f of A is positive and f of B is negative, or the other way around. If that is the case, by the intermediate value theorem, which we didn't prove but we just had a quick look at last week, there must be a point in between A and B such that f of that point equals 0. Okay, and that's our root. So or must lie between A and B in that case. Okay. So that's what we learned, and it's a very simple check. You just find A and B such that FA multiplied by FB is negative. If that is the case, there must be a root somewhere between A and B. And we don't know where that root is, so we guess. We say the root is halfway between the two, at A plus B over 2. So hence the name, the bisection method. We bisect this interval. And here's our estimate. C is there. Okay. Then we will prove this. Either we now have two intervals. I should have gone back to where I was. Apologies. Jumping around here in my slides. One of two things now happens. Either A and C bracket a root. In other words, the root is somewhere between A and C, or alternatively, C and B bracket a root. It's very easy to check. We do the same check before. If the product FA multiplied by FC is negative, then the root or is between A and C. If the product FA times FC is positive, that means the root is not between A and C. It must be between C and B. It's a very quick, simple check. In this particular example, the root is between A and C. So what do we do? Having found out that the root is somewhere between A and C, we still don't know where it is, but now we know it's between A and C. We replace B with C, so C becomes the new B. We've halved our interval. Our interval was twice as big. Now our interval only runs from here to here, and we repeat the process. We now have a new interval, half as big. We find a new midpoint, and we keep on going. There's our new midpoint, and then we either replace A with C or B with C. In this case, we'll replace A with C because the root, a simple check will tell us that the root is somewhere between C and B. And we end replacing A with C, like that. Okay, so that's the bisection method. Really simple, and really simple to code as well. Very simple. We'll code it up later on. We'll apply it. Works very well. Very robust. It'll generally work. It's just stupid. It's kind of nice. It's like a dog. So it just does its stuff and doesn't ask too many questions, and is very dogged, and will eventually get to a root, no matter how slowly. It will eventually get there. So the problem is it's quite slow. It's not as fast as it could be. And so instead, if you want to make something more efficient, we said, well, the bisection method is good, but let's find something more efficient. Let's derive what's called the Newton-Raphson method. And the Newton-Raphson method is, well, the bisection method is more like a dog, the bisection method is a dog, the Newton-Raphson method is a cat. It's a bit more temperamental. It can kind of turn on you. It can treat you very badly. It can fail spectacularly, work very badly. But generally it's more sophisticated and is smarter. So how is it smarter? Well, it's smarter because rather than just taking an interval and halving it every time, the Newton-Raphson method inject some intelligence into the situation. Inject some intelligence into the situation by trying to find the root in a more structured way. Okay, so we did some analysis last week. We did this late on a Tuesday. We were all falling asleep. I won't do it all again, but I'll just give you the story, the headlines of what we were trying to achieve. So what we do is we have an input-output method, and what does that do? It takes an initial guess, x0. That could be any guess you want, okay? Any guess you want. And then it updates it and makes x1, x2, x3, x4, x5 in such a way that x1, x2, x3, x4, x5 is getting progressively closer to the unknown root. How is that the case? We'll see why that is the case later on. How do you go from x0 to x1 and x1 to x2 and in general from xn to xn plus 1? It's very simple. You take xn, your present guess, you work out the function value at xn, which is f of xn. You multiply that by some number beta, and we'll discuss that now in a second. You add that to xn, and that generates your next guess, okay? And hopefully, if you've done right, your next guess, xn plus 1, will be better than your previous guess, xn. That doesn't happen automatically. You have to pick a clever value of beta in order for that to happen. If you put in a bad value of beta, there's absolutely no reason your next guess will be anywhere nearer the root than your previous guess. You have to pick a smart value of beta. But if you do pick a smart value of beta, you can ensure that your next guess, xn plus 1, will be closer than your previous guess. Okay. How do we pick beta? Well, we'll do some analysis. We use the Taylor series. We apply the Taylor series to this expression here at the bottom of this slide. So this expression here is kicking off what's called our error analysis. What we do is we say, let's imagine that at step n, our estimate is xn. We know what that is because we are running the code. We know what xn is. We don't know the root, and we don't know, therefore, if we don't know the root, we don't know how close we are to the root. But the difference between the unknown root and our known guess is this unknown quantity here called the error, which is epsilon n. So xn is known, and we can decompose it as the root, which we don't know, and the error, which we don't know, epsilon n. And we would like to make the error as small as possible. The error goes to 0, happy days, xn goes to r. So how can we analyze this? Well, take this error decomposition and put it into our input-output update, and we get our n plus 1th guess is now equal to our nth guess, where we've put in our error expression, or plus epsilon n instead of xn, plus beta times f of xn. Okay, that's the first thing we do. Now the problem is we want to choose beta, which means we've got to do something clever with this term here. The problem is we don't know r, we don't know epsilon n. So how can we write down something clever about this term if we don't know r and we don't know epsilon n? Well, what we can do is we can use the Taylor series. And the Taylor series does the following. Let's skip through the example. We did this last Tuesday, so I won't do all this again. But the Taylor series enables us to take a function evaluated at a input close to a. Here is some input a. Here is a plus h. So h is thought to be small here. So a plus h is some input which is close to a. And we can say that the output at a plus h, we can write it in terms of what's happening at a itself. So we say that the output at a plus h is equal to the output at a, f of a, plus some correction terms. Correction terms are h times the first derivative at a, plus h squared over 2 times the second derivative at a, plus h cubed over 6 times the third derivative of a, and so on. So we can express what's happening at a point close to a in terms of what's happening at a and the derivatives at a. First derivative, second derivative, third derivative. We add all these terms up. If you add them up properly, the more terms you add, the closer and closer this becomes to this quantity here. It's guaranteed. It's a Taylor series. Problem is you need an infinite number of these terms before you exactly get this. And in practice, we don't do an infinite number. What we do is we take maybe a finite number and truncate it, and we approximate it. That's the Taylor series. Very, very useful. We can apply it case because in our input-output relationship, we have f evaluated at the unknown root plus unknown error is f of xn. And this is exactly the same form as above, with a equals r and h equals epsilon n. And we can therefore write that in terms of what's happening at r. This expression is equal to the function value at r, which happens to be 0. We'll leave it in for the time being, but it will be 0. Plus the first derivative, second derivative information, all scaled by the error term squared, etc. We introduced this notation, big O, because this can quickly get out of hand, all these infinite number of terms. So what we do is we take all of these terms with epsilon n squared, epsilon n cubed, so anything with a power greater than or equal to 2 of epsilon n, and we just dump them all together in this bag, and we label this bag order epsilon n squared. And what that means is, well, epsilon n is small, so that means epsilon n squared is pretty small. Epsilon n cubed is really small, epsilon n to the 4 is really, really small, and so forth. There's a whole infinite number of terms here, and they're getting smaller and smaller and smaller and smaller. We lump them all together, put a label on the bag saying, here's a whole bunch of things, they're very small, and the largest term you're going to find is of the form some constant times epsilon n squared. Okay, this is the largest term. There'll be a whole bunch of smaller terms, but this is the biggest. And this notation just means we can take all this stuff, and without worrying too much about the detail, we can just put it all in this little container and ignore it. Okay, provided we're a little bit careful with it. That's that. What we do is then we can say that this is our new expression. We put what we just had into input-output. Now our new expression for our new estimate is xn plus 1. It's equal to what we had before. We had f of r plus epsilon n. We put in our Taylor series, rearrange it. This is what we get. And now we know that if we can make what's in this bracket here, 1 plus beta f dash r, if we can make this small, we can make this term disappear, or make it very small, which would be great. That means our previous error was epsilon n. If we can make this term go away, our new error, well, xn plus 1 will be r plus all this stuff. And this stuff is order n epsilon n squared. But the previous error was epsilon n, which is pretty small. If we can make this expression disappear, our new error will be epsilon n squared, which is even less. Okay? Because for small epsilon n squared is much smaller than epsilon n. Problem is, we don't know how to choose beta because we're stuck again. We don't know what f dash r is. We don't know what r is. R is the root. We don't know what r is. We can't say anything about this. So what we did last week is we took r and said, well, r is equal to our present estimate minus our present error, epsilon n. Okay. And we can use a Taylor's expansion based on that. Therefore, f dash r is equal to f dash evaluates our present value, our present estimate, minus epsilon n. And use a Taylor series expansion for that. We get all this stuff. And this is what we did have. This is what we get. Okay? Which we can simplify and simplify and simplify. This is what we get. So our new estimate is equal to the actual value plus the previous error multiplied by this thing here, plus a whole bunch of smaller error terms, which are an order of magnitude smaller than this guy here. So it would be great if we could choose beta to make this thing disappear. And we can. We can choose beta is equal to minus 1 or f dash xn. That will make this thing add to 0, which makes this term disappear, which solves our problem. The choice of beta, therefore, is that, in which case this term goes to 0, and the error becomes order epsilon n squared. So it was epsilon n, which was a small number, 0.1 or so. It becomes epsilon n squared, which is 0.1 squared, 0.01, even smaller. Okay? And we can do this because we can make beta equal this because we know xn, it's our present estimate. Good. And when we do that, we get the Newton-Raphson method. So as I explained on Tuesday, 102 slides. This is the only thing you need in order to do a certain one is this stuff. You need a little bit more. But, if you want to understand this, you need all 102 slides. If you want to just do it, this is all you do. I suggest you try and understand it, because in the class test I'll be asking you to explain that kind of stuff. But for your assignment, Really, it boils down to this and some termination criteria and some stuff like that. Okay, doke, so we finished on Tuesday by applying this. Let's work out the square root of 2. We know the square root of 2. That's just for illustration's sake. Let's use Newton-Raphson to work out the square root of 2. So we make a function, x squared minus c. The root of this function will be the square root of c. Okay? Because when c is equal to the square root of c, we're going to get x squared minus c, which is 0. It's a root. If the function is this, it has a root at the square root of c. The derivative, because we need the derivative for the Newton-Raphson method, is f dash x is equal to 2x. Raphson says that the updated iteration is the previous iteration minus f of xn divided by f dash at xn, which is this, and you can simplify it to get that. Lo and behold, starting off with xn equals 1, this is, we put c is equal to 2 to get the square root of 2. Let's start with an answer which is not the root. 1 is not the square root of 2. But we start at our initial guess at 1. First update will be a half 1 plus 2 over 1, which is a half of 3, which is 1.5. Okay. First update is 1.5. So we go from 1, our initial guess, to 1.5. It's a good update because the actual answer, root 2, is about 1.414. So in a single step, it's got a good bit closer. You stick 1.5 into this updating expression again, you get 1.416666666 forever. Stick that back in, on and on and on. You get 1.414213, blah, 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 after 4 updates. And we are correct to how many decimal places? About 9, 10, 11, count to 0. So after only 4 steps, you pretty much got it to machine accuracy. Okay. A word about the error analysis. We said our error analysis suggests that the error at step n plus 1 is equal to the error at step n squared, or proportional to it. It isn't equal to it, but it's proportional to it. And we can check that here. We can say here's the error at step n compared to the square of the error at the previous step. And we see after a couple of steps it converges to a constant, 0.353 or so. So what this is telling us is that the more steps we take here, the error at the nth step is pretty much 0.353 times the square of the error at the last step, which is what was suggested to us by our error analysis. Okay, we stopped there on Tuesday because I think we were all at the keel over for 2 hours. Has anybody got any questions about what we did on Tuesday? I'm happy enough for that. That was just a little recap of it. Happy enough? NUIM, how are you? Any questions over there? Ben is just explaining people missing an NUIM at work placement, so thanks, Ben. Any questions at NUIM? That's just a review of what we did on Tuesday, so let's on then, so, and do a little bit more. You guys are engineers, so this is an algorithm, and I expect you to be able to apply this. Again, your granny can apply this. But you guys are engineers, I expect you to be able to understand it as well, because that's the key to making this work well and designing things in an efficient way, and making sure that everything works, rather than just applying algorithms blindly, understanding what they're doing. So what is this thing doing? We've derived it in a rather abstract way using error analysis and Taylor series, and that works. It's not particularly illuminating. It doesn't tell us, it doesn't make a nice picture of why this works. Explains mathematically why it works, but it doesn't give us a nice picture. Let's try and derive a nice picture of why the Taylor series works, or the Newton-Raphson works, rather. So what the Newton-Raphson method is doing, it's often called the Newton method. It should be called the Newton-Raphson method because it was independently developed by a guy called Raphson. The more you learn about Isaac Newton, the more you realize it's actually pretty nasty. He was a nasty character. He used to throw his weight around and try and intimidate other people who would have discovered things around the same time as him and try and claim all the credit for himself. Because Leibniz, the German, would have discovered calculus at the same time. But Newton's name is associated with calculus more than Leibniz, again because he was quite preeminent at the time. And apparently he was quite a nasty character. He had a big row with Robert Hooke. He used to make fun of his appearance and all kinds of stuff, so he was a nasty character. So I should really call it Newton-Raphson. I shouldn't let him away with that. But so the Newton-Raphson method, what does it do? Well, we're seeing what the algorithm says, and what's happening. let's imagine we have a function here in black. Okay, here's the inputs, here's the outputs, here's the curve in black. We can, we have the function form. We know what fx does, but we don't know the root. We don't know where r is. So we have a guess, x0, which is here. And x0 is not the root because f of x0 is equal to some number up here. It certainly isn't 0. How can we improve it? Newton-Raphson says, well, we update it by taking away f of x0 divided by f dash of x0. Okay, that's what the update is. It's x1 is equal to x0 minus f of x0 over f dash of x0. Well, f dash of x0, what is that? Well, f dash of x0 is the slope of the tangent to the black curve at the point x0, f x0. So this point here is on the curve. It's equal to x0, f of x0. And we can define a tangent to the curve at that point. And the tangent to the curve is basically a local linear approximation to the curve. The curve is not a straight line, but if we were to approximate it as a straight line at this point, when we're zooming in on it, the straight line we would get would be this. It's called a tangent. We continue the tangent down as far as the x-axis. It intersects the x-axis and it makes this angle here alpha 0. Okay. And the derivative f dash evaluated at x0 happens to be equal to the tan of this angle. It's the slope of this line, which happens to be the tan of this angle. Okay. So that's, we know that from first year. That's what the definition of a derivative is. Okay. It's the tan of this angle here. Okay. How does that help us? Well, but the tan of this angle is equal to the opposite, which is f of x0, divided by this amount here, which we call it h. Okay? So tan of alpha 0, so this df dx, is equal to this opposite distance, which is just a function value, divided by h. So therefore h, just rearranging this, is equal to f of x0 over tan, which in turn is f of x0 over f dash. And this is the update that we do in Newton-Raphson. We start off at x0 and we take away fx0 divided by f dash x0. We take this away from x0. In other words, we start at x0, we take away h, we go from x0, we go to there. That's x1. Okay. So from a graphical perspective, what Newton-Raphson does is it takes x0, it works out f of x0 is this point here. It works out the tangent to the curve at this point. The tangent is a linear approximation to the curve, and it says if this curve was a straight line, which it's not, but if it was a straight line, we could follow this straight line down as far as here, and this would be the root. So Newton-Raphson says, let's take the curve, approximate as a straight line, and find the root of that straight line. We get to here. So it rides the tangent until we get down to the x-axis here. And that's our updated guess. That's one. Okay. Then it does it again. This is just a word I've just been saying. x1 is equal to x0 minus this correction. This correction is just this distance h. So we go from x0 to here. We start at this point. We slide down the tangent until we get to here. And this gives us... Then we do it again. We go x1. We get to f of x1 is here. We work out the slope of the tangent of the curve at this point. We say if this curve was a straight line, it's not a straight line, but if it were a straight line, we could ride this tangent down. This would be the root, x1. And we see that by following these tangents down to the x-axis repeatedly, we're taking these big steps closer and closer to the actual root itself. So here in 2 steps, we've got from here over to here, and we're pretty close to the root. Okay. You can see that. This is an alternative way of deriving the Newton-Raphson method. You don't need to do all your error analysis stuff. The error analysis stuff is good because it tells you how well this works. But in terms of choosing a beta, choosing a good value of beta, you could derive Newton-Raphson just by arguing along these lines. This is a sensible thing to do, and it's equivalent to Newton-Raphson. Okay. Any questions about that? How are you doing, NUIM? Any questions? How are you? Question? if x2 is on the left of r, what would happen? Is that your question? Okay, so the question is, if the form of the curve was such that the tangent had not brought us to this point, but maybe it had overshot, if we'd arrived over here, to the left of r, what would happen? And the answer is, well, if x of 2, if we overshot and our next estimate was here, we would continue with the process. The tangent now would have a positive slope, and we would follow, what would it be? We would see that the function value of x2 would be negative. So the correction step would be a positive correction step. So we would go, we'd increase, we would go this way. So here the correction step is negative because the slope is positive. Let's just see, it's a negative correction, it's minus this. These quantities are both positive, so the correction step is minus. If we overshot in this particular case, f of x2 would be negative and the correction would be positive, and we would start going this way. So it is possible, you can oscillate back and forth around the root in this case. You don't always approach the root, you don't creep on it from one side alone. You can overshoot, you can oscillate back and forth several times, getting closer every time. Okay, that's a good question. Any other questions? NUIM, any questions over there? You happy? Send me a chat, tell me you're happy. So know that you're alive. So here's some little informational details about Newton-Raphson. I said all you need to know is really on one slide there. Not quite. There's a couple of little things which make it a little bit more good stuff. Everyone's alive in a minute. Thank you. Few things we should know. In order to apply Newton's method, we need a knowledge of the function. We need to be able to work out of x. So we need to know what function is, okay, for a start. Ideally, we also need to know the first derivative of the function. Okay, we need to know what f dash is, because that's part of the update process. Now that makes it a little bit tricky, because if we don't have, or if we have a very complicated function, which is very difficult to differentiate, and there's lots of engineering functions which are very, very difficult to differentiate, how can we do this? We can't do f dash. Now, what we can do instead is, we're going to see this in handout number 1. So I've tried to approach these handouts in an order to let you do your assignment, but consequently, this little thing we haven't covered yet. It's in handout number 1. We'll be doing this in great detail. But very simply stated, if you can't work out f dash explicitly because the function is really complicated and you can't figure out what the derivative is, you can approximate f dash by some finite difference. And this is called a forward finite difference, forward approximation. Okay? We're going to cover this in great detail in handout number 1. But for the time being, we know that the derivative of f is equal to the limit as h goes to 0 of an expression like this. That's the actual exact derivative. If we can't do that exactly, what we can do is we can just stick in to this expression a very small value of h. It's not a limit as h goes to 0, but if h is very small, this will be an approximation to the limit. And therefore, this will be an approximation, hence the little squiggly equals here, which means approximately. This will be approximately equal to this. Okay? So in the absence of knowledge of the derivative, we can approximate the derivative by doing this finite difference approximation, which is nice because it just requires knowledge of f dash. It only requires being able to work out f as xn and at xn plus a little bit. And we choose a small value. We'll do this in more detail next week. This is called the secant method. If you replace f dash xn with this in the Newton-Raphson algorithm, you get something that looks like this instead. Okay. This is called the secant method. Geometrically, it's very similar. In the Newton-Raphson method, at x0, we work out the actual tangent to the curve at x0, and we follow that tangent down. Using the secant method, we approximate the tangent. We look at x0 plus h, where h should be a very small amount. I've made it relatively big here so you can see it on the screen, but in practice it should be very small. And the straight line between these two function outputs gives us an approximation to the tangent. It's not equal to the tangent, it's an approximation to it. And we can use this secant and we can follow the secant down until we get to x1. That's going to be pretty good. Now it turns out that this is as good as the Newton-Raphson method. Okay? in terms of errors, provided h is small, you've got a good estimate for f dash. This is going to work pretty well. Okay. Now, other little implementational issues about Newton-Raphson. We've got to know when to finish. We kicked it off with x0, then we made x1, then we made x2, then we made x3. When do we stop? What point do we stop? Well, in our algorithm, we had a little while loop, and we said while f of xn was less than some delta. So in other words, we keep on going until we get an estimate for a root xn such that f of xn is very small. We will never, ever find an xn, I shouldn't say never, ever, it's very, very unlikely that we will find an f of xn such that f of xn is equal to 0. Because we're working with a finite precision machine, there's going to be round-off error. And even if there wasn't round-off error, this process could take a long time because you're looking to hit a individual point on a continuum, which is effectively impossible to do. So you're never going to find the actual root. The best you can do is find an xn which is very close to the root, and you know you'll be close to the root because f of xn will be very small. It'll either be very small and positive or very small and negative, one way or the other, and we don't care whether it's positive or negative. So you can terminate when xn is such that f of xn is really small. So you can do a little while loop, and when that happens, you terminate. Alternatively, you can say, well, if the update is no longer very big, if xn goes to xn plus 1, but xn plus 1 is pretty much the same as xn, if you look at the input-output relationship, that must mean that beta times f of xn is very small, which means we're close to a root. So this is, condition 2 here is effectively the same as condition 1. It's supposed to be a scaled version of it. Okay? So either the output of xn is small or our increment between this step and the previous step is very small. Or alternatively, and this is going to be careful here because these methods can fail. We said the bisection method plows on, always gives you an answer, or almost always gives you an answer. These ones can blow up in your face a little bit, so be a little bit careful. So it's good practice to maybe put in a specified maximum number of iterations and say, if this hasn't happened and this hasn't happened, fail out after 100 guesses or 1,000 guesses or whatever, however much patience you have, okay? Another thing to be aware of in terms of implementation is that if f of x has more than one root, and most functions of interest will have more than one root, the same choice of x0 will always lead to the same root. If you start this algorithm with the same x0, it always goes to the same root. So to find all the different roots, you got to run the algorithm many times with different x0. And that's a little bit of pot luck involved there, because many x0s, many different x0s can all lead to the same root, as you will find out in assignment number 1, which is based on that observation. Some difficulties. Anybody tell me? Give me the answer there, but in case you didn't see it. Where's the algorithm there? Here's the algorithm here, okay? x1, or in general, xn plus 1 is equal to xn minus f of xn over f dash xn. Can anybody tell me when will we have trouble with this algorithm? When will the algorithm fall over and fail? Yeah, when the slope is 0. Exactly. So 2 ways we can think about it. So the observation is if f dash of xn is equal to 0, actually, these guys, let's go back for a second until I find, here's our algorithm, okay? If f dash of xn is equal to 0, this is going to explode because we're going to divide by 0 here, which is not defined, and the algorithm is going to crash, okay? So if f dash x of n is equal to 0, we're going to be in trouble. Even if f dash xn is not equal to 0, because again, the chances of finding a point such that f dash xn is precisely 0 is kind of small. Even if this is only very, very small, if it's close to 0, this would be a very large number. And you will have gone from xn, the correction step would be huge, and you go flying off up the x-axis towards plus infinity or minus infinity, away from the root. Okay? So that is a problem with the Newton-Raphson method that you have to guard against. You've got to be careful with that. So geometrically, graphically, let's have a quick look at what that does. Okay, here we go, yes. Here is the situation. If f dash x is very small or 0 at xn, we have a problem. Okay, and the problem is this. Here is xn. We have a function that looks like this. F dash xn equals 0 means that the slope of the tangent is 0, which means that the tangent is horizontal. Horizontal line has slope 0. So if it has slope 0 and we go up here, remember graphically what we're doing is we're updated estimate. Well, if the tangent is horizontal, we slide down the tangent. Where do we go? We just slide off to infinity. We never slide all the way down to the x-axis. So this just never intersects. Okay? Even if this is non-zero, if it's close to 0, we slide down this tangent. We're going to slide somewhere way, 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 way over to the left or way, way over to the right, very far away from here. So we're in trouble. And there's no way of avoiding that in Newton-Raphson. If you find yourself with an estimate such that f dash xn is equal to 0 or close to 0, you're in trouble. So you have to maybe put in a little bit of intelligence into your code to maybe do something else at that point, to check for that. And if that happens, to maybe just randomly jump a little bit away from there or do something. Maybe use a bisection method for a couple of steps or something else. Okay? So there's ways around it, but you guys will figure out that. You don't need to do that for your assignment, but just in general if you're putting this up. This is particularly troublesome if near fx equals 0, near the root, if the values of f dash of x are very small near the root itself. So if f dash or is equal to 0, that means f dash x will be close to 0 near the root. Which means we have a situation like this. Here's the root, and it's got a very flat curve in the vicinity of the root. Okay? So if you had a function like x to the 10, for example, or x to the 100, it would look a little bit like this. It has a root at 0, but is very, very, very flat in and around 0. So any estimate to the root that you get in and around here is going to fall foul of this f dash xn being very small, and the update is going to shoot away to infinity. So this is an ill-conditioned problem. It's hard to get close to the root here because the closer you get to the root, the smaller f dash xn becomes, and the further away you get thrown from the root. So this is just a difficult problem to solve even Newton. You've got to be aware of those. They're little implementation things. You can code up Newton-Raphson and then it mightn't work. You might be scratching your head, why didn't it work? But perhaps if it doesn't work, perhaps you've got a situation like this. Okay? Very good. That concludes that handout. You now know all you need to know about Newton-Raphson methods. Has anybody got any questions before we park that? How about you, Malouth? Still kicking. We fine here. You're great. That was 20 minutes ago. You still okay? Any questions? Okay, so my next question, we have a choice. That's an hour. We're going to break in about 45 minutes. Next 45 minutes, I'm going to ask the French students, what would you rather do? We can do, because you're going to miss the last part. Okay? You can see it on the recording. But, so you have a choice. What we can do now is we can do some MATLAB, some examples of this stuff. We can make a MATLAB code to do the ray tracing problem that we were looking at, trying to find the reflection point. And we can make a MATLAB code to make a factor. Okay, we can do that now. Or alternatively, I can move on to the new handout on integration, which you need for assignment 3. I'm anxious to get to tell you all you need to know about doing your assignment. So I'm going to cover both of those things in the next 2 hours, but the French guys, you've got to go, of course. So you can only see one of the two. So which one would you rather do? Do you want to do some MATLAB, or do you want to see the handout integration? MATLAB. Okay, I'm going to do some MATLAB examples NUIM. Okay, so that's going to require me to set up a computer here for about 5 minutes. Let's take a break for 5 minutes. I'm going to set up MATLAB on this computer and change presenters, okay? So, you see that anyway, I'm okay? Yeah, okay, good. So, the problem from optics, we have a transmitter, so it's two-dimensional space, x, y. Here's the origin, 0, 0. We could do it in 3D, but let's just do it in 2D. X values this way, y values this way, okay? Origin here, someone's placed a transmitter here at some position, xy space. Someone placed a receiver here. The receiver is here, again, somewhere else at xy space. This is a semicircle, reflecting structure, could be whatever geometry, but let's assume it's a semicircle just for this example. And we would like to find the position or positions along the semicircle such that a reflection occurs. Okay? So we don't know how to do this by hand. So we've got to do numerical methods to do it. Okay? So what we do is we say that all possible points along this semicircle are parameterized by this value phi. Okay, so if phi is equal to 0, we're at this point here. And as phi changes, we have x is equal to r cos phi, y is equal to r sine phi, and as phi changes, we have all these possible points along here. And phi is pi over 2 at this point, and then phi is equal to pi at this point. So by varying phi between 0 and pi, we can set through all possible points on the semicircle. And our challenge is to find the value of phi that gives us some point on this semicircle, such that if you draw a vector from that point to the transmitter and draw a vector from that point to the receiver, these are the vectors we see here, v1 and v2, and we examine the angle that these vectors make with the normal. This is the normal of this point, which is given by minus cosine phi x minus sine phi y. The normal, or the angle these vectors make with the normal, is theta I and theta r respectively. And if we can find a point such that theta I and theta r are the same, angle of incidence in equals angle of incidence out, therefore we have a reflection point. That's our challenge. So we need to define a function f, which is the difference between theta I and theta r as functions of phi. We've got to find the root of f in terms of phi. If we find a root of f, it means we found a situation where this is equal to 0, angle in equals angle out, which means we found a reflection point. This in the diagram is not a reflection point, because theta I and theta r are obviously very different, but in general, you can find that. So we're going to use MATLAB to do this. And I've written the code. I'm just going to explain the code. You see this okay in UIM? Okay, thank you guys. So, how will we do it? I'm not going to write this in front of you. I wrote this myself. Let's go through it and explain it. I will put this code on the website so you can study it at your later on, okay? And I will comment it. Everyone should comment. I never comment. I give out to my students for not commenting, and then I never comment myself, but there you go. First, we clear all variables. Always good practice for starting a new simulation. Close all windows. Again, good practice. Don't get confused. CLC just brings the workspace. It clears it brings the cursor back to the top of the screen. It just makes it nice. Okay. First thing we do is let's specify where our transmitter is. S here means source. So the source has an x coordinate of -2 and a y coordinate of -2. These are things we can change. Let's leave the source at -2, -2. The receiver, again, we can change the receiver, and we'll run this for many different receiver points. Receiver is x coordinate 2, y coordinate -4. So it's a little bit to the right. It's broadly as in the diagram we were just looking at. Okay? The semicircle is centered at 0, 0 and has radius 2. The first thing we're going to do is draw a picture of the semicircle and the transmitter and the receiver, just so we can see how things are. So to do that, we need to make a little vector containing samples of the semicircle. Let's make 200 samples the semicircle. Let's have n equals 200. Now the semicircle, as we explained, is made up of points where phi varies from 0 to pi. Okay? So we're going to have a total phi increment of pi. We'll take n steps to do so. Delta phi, should we call it delta? Here. We just delta phi for things nice and consistent in terms of our diagram. Now delta phi is a different thing later on. I'm going to use this later. Come back to him. I have coded up the Newton-Raphson method and I've coded up the dissection method. So let's first of all say we're not going to use the Newton-Raphson. We don't use the Newton-Raphson, we are going to use dissection. One is 1 minus 2. We're going to use dissection first. The first thing is this little loop here, for loop, has a counter going from 1 to n. Okay? And it steps through, again, we should just be a little bit careful here. Let's call it phi. So we step through n steps. We set n to be 200. For every n, we work out phi, and we work out a point on the circle whose x coordinate and y coordinate is given by or cosine phi or sine phi. And after this, make 200 points, which when we plot them together, we'll make the semicircle. Then we make a figure. We plot this array holding the x values and the y values of the points on the semicircle. We hold. So hold on is a request to MATLAB to keep this figure and to overlay the following plots on top of this plot, so we don't get 3 separate plots. So we plot the source coordinates in red with a star. We plot the receiver coordinates in green with a star. Okay. That's the first part of the code, which just makes a picture. Now, next thing we do is we say, let's find the reflection point. So we need a little indicator to tell us when we found the root. So we have a little variable, we say found root. We set it equal to 0 because we haven't found the root yet. It starts off at 0. When we find a root, we'll change this to 1. Right now it's 0, indicating we haven't found a root yet. We need a threshold because this is a numerical process. We're not going to find root exactly, so we're going to find it within a threshold. A threshold being a small number. If Newton-Raphson equals 1, then we do all this stuff. So let's zip through this stuff and let's look at the dissection method first of all. Okay. Let's go down to here. If used bisection equals 1, which is what we've decided, what we do is to do the bisection method, we first of all need to bracket a root. Now we need an a and a b such that there's a root somewhere between a and a b. So we'll have a is equal to 0. That's a point on the right-hand side of the semicircle. B is equal to pi. That's an angle phi equals pi. That corresponds to a point on the left side of the semicircle. We need to find out if this brackets a root. We need to know f evaluated at a and f evaluated at b. Okay, so let's go back here, where at least we can find it. Okay. So f is given by theta I minus theta r. Okay, so we need a little function to work out f. Now what is theta I? Well, theta I is obtained by taking the dot product of where V1 is a vector from a potential reflection point to the transmitter. We call that V1, it's a vector. So a vector is just, in 2D, it's just an x-coordinate and a y-coordinate. It's the difference in the x-coordinate between here and here, the difference in the y-coordinate between here and here. Okay, so it's just a vector in 2D. That's V1, the vector. N hat is the normal at this potential reflection point. This potential reflection point has value phi. The normal is given like this. It has an x-coordinate and a y-coordinate. That's a vector. So V1 is a vector, N hat is a vector. We can get the dot product. Multiply the x-coordinates together, multiply the y-coordinates together. Okay? And the dot product gives us cosine of the angle between them. Right. Provided we normalize V1. We divide by V1 magnitude. This is the magnitude of V1 to ensure that this is a unit vector and the normal is already a unit vector. Because normal is a unit vector. So we divide by this to make this a unit vector. So this dot product now gives us the angle between the unit vector V1 and the unit normal, which is cosine theta I. So to get theta I, we take cosine inverse of this. So the dot product gives us cosine theta. So to get theta, we take cosine inverse of this. Okay? Similarly, for theta or, we do the same thing, but we use V2, which is a vector from here to the receiver. And we get V2 dotted, and we normalize V2, we divide it by its magnitude to make it a unit vector. V2 dot n is now a unit vector times a unit vector, and it gives us cosine of the angle between the two vectors. This is here supposed to denote the normal, 1/2, okay? In there somewhere. And so V2 divided by its magnitude dotted with n hat gives us cosine of the angle between them. To take the inverse cosine of that to get the angle. So this is a way of getting theta I, and it's a way of getting theta R. Okay. Once we do that, we can take one away from the other. That gives us F. So in order to make these things, what do we need? We need V1. We need information about n. We need some bits and pieces of this. We need to know, to make V1, we need to know XS and YS, the source X and Y location. To make V2, we need XR and YR, which is the receiver X and Y location. So what we do is back in our MATLAB code, where's it gone? I have a function. I shall open it now. Called comp F value, which computes the F value, and we feed it with the information it needs. To make this F value, we need to know where the transmitter is, so we can make vector V1. We need to know where the receiver is, so we can make vector V2. And we need to know R, to know the point in question on the semicircle, and we need our present guess for phi. So in the bisection method, we start off with one value of phi is 0, one value of phi is pi, and we feed these in as well. So we get the function value evaluated at A is equal to comp value with all these inputs, and the function value at B is comp F value with all these inputs. And let's have a quick look at comp F value just to reassure ourselves that it does what that slide says. So it reads in all these numbers. It makes the XY location on the semicircle, or cosine phi gives us the X location on the semicircle, or sine phi gives us the Y location on the semicircle. We work out the normal. We need to know the normal to get the dot product. X coordinate of the normal, Y coordinate of the normal. We work out the vector V1, which is just its X coordinate is the X coordinate of the source minus the X coordinate on the semicircle, the Y coordinate similar. We work out V2 is the difference between the X coordinate of the receiver minus the X coordinate on the semicircle, similarly for the Y. That gives us V1 and V2. Theta I, according to a formula, we take the dot product V1 and n. So we multiply the X coordinates together, we multiply the Y coordinates together. We normalize, we divide by the magnitude of V1 here. This dot product gives us cosine theta I, and we take A cos. A cos is the MATLAB command for inverse cos. This will now return a angle between 0 and 2 pi. Okay. That's theta I. Do the same for theta R, and then the result F is the difference between theta I and theta R. This is the thing we want to be 0. If this is equal to 0, we found a root. That's all that. Let's go back to our rate trace. So using the bisection method, we have a guess for A, a guess for B. We work out F of A, we work out F of B, and we check. While F of A times F of B is greater than 0. Well, if the product is greater than 0, it means they're both on the same side. They're both either positive or they're both negative. Okay, so it means there is not a root between them. So while this is the case, it means there is not a root between A and B. And what we do is we take B, B was pi, come back over a little bit. We take away pi over 10. We get a new value for B. Okay? and we work out a new value of f of b. And then we check whether fa times fb is negative now. If it's not negative, we haven't bracketed the root, and we keep on going. We keep on going until we find the value of b such that fa fb is negative. That means there's a root between a and b. A is a value of phi given by 0. B is a value of phi originally set to pi, but then made smaller and smaller and smaller until we find the b such that there's a root in between the two bits. Good. That's that. If fa fb is less than 0, we just print to the screen. We say root is bracketed between these 5 values, a and b. If this while loop couldn't find an a and b, the bracketed root, it will only go so far. It won't keep on trying. It will eventually track out, and it will say could not bracket root. And we know that we have a problem. We couldn't start the bisection method because we couldn't bracket root. Let's be positive. Let's assume that we could bracket root. So let's imagine we have bracketed a root. We have the midpoint is a plus b over 2. So what we do now is, if you remember the bisection algorithm, what do we have to do? We have to choose to either replace a with c or to replace b with c. And the way we do that is we compute f evaluated at c. So we have this code comp f value. We feed in the angle phi is equal to c into it. We get a number. And then we check and see, well, if fa times f of c is negative, it means a and c bracket a root, which means we can replace b with c. Otherwise, if it's positive, it means b and c bracket a root, in which case we replace a with c. Okay, so this is our two cases. And we do either one or the other, and then we make a smaller interval, and then we make a new midpoint based on that. And we keep on doing this. This while loop says keep on doing this while the absolute value of f of c is greater than the threshold. So the threshold is where we stop. So once this f of c gets smaller than the threshold, it means f of c is very, very small. It's pretty much 0. We stop. And that's our estimate for the root. Okay, people happy enough? So this is dissection algorithm here, this little bit. What we do is, if we left that little while loop, and if we did manage to find a root, if absolute value of f of c was less than the threshold, it means c is a value such that f of c is very small d. It's effectively a root. We put our little flag, found root equals 1, to tell us we found the root, and we say our phi guess was equal to c. Okay, so that's the end of that little section. What do? We display it on screen. If found root was equal to 1, we get the coordinates on the semicircle of our root, of our reflection point. So answer x is r times cosine our phi guess, which is the where we found the root. Answer y is equal to r times sine of that. Okay? This is our reflection point. Really use it to call that something different. Call it reflection point to make it a bit more meaningful. You should always try and use meaningful variable names, because in a year's time when you come to look at this, you want to know what everything does. You should use meaningful names. That's that. And then what we do is we just make a little, we take our figure. Remember, this code will make a figure with the semicircle, the source, and the receiver. We make a little straight line from the source to the reflection point. Okay. and then a segment from the reflection point to the receiver, just so we can see the ray going from the source to the reflection point to the receiver. And then we plot that little segment there. And then we plot the reflection point on the figure. Okay, so that's the bisection algorithm. Let's run it. Let's hope it works. Worked the other night, so it should work now. Oh, what am I doing? Yes, okay. Okay, there we go. So this is the output. Here's our semicircle. We took 200 little samples and we made the semicircle. That we plotted. We plotted the transmitter here in red, the receiver here in green. The bisection method started off with A equals this point, phi is equal to 0, B is equal to this point, and phi was equal to pi. It found a route between A and B. It didn't update B. A and B, our initial guess for A and B bracketed a route between them, so it didn't have to refine that at all. It then, A and B bracketed a route. A corresponds to phi is 0, B corresponds to phi is equal to pi. The first C would have been pi over 2, would have been a point here at the top. It would have found that this point and this point brackets a route, so B, which was equal to phi equal pi, would have been replaced with phi is equal to pi over 2. Oh yeah. Right? I'm not sure, thank you. A was here, phi is equal to 0. B was here, phi is equal to pi. Okay. It bracketed a route between them. The first midpoint would be pi over 2, which corresponds to C being here. If we do a test, we would have found that C and A bracket a route. So B would have been replaced by this here. And then we would have got a midpoint somewhere between phi is 0 and phi is pi over 2. We would have got a midpoint of phi over 4. This would have been our new midpoint. And we would have replaced A with this midpoint between here and here, and so on and so forth. We would have kept halving these midpoints, or halving these segments in size every time, until we got to a segment so small that the midpoint of it satisfied Fresnel's law for reflection. Okay? And we would have crashed out, and it would have returned this as an answer. And then just to show it on the screen, we just draw a little segment from here to here and here to here, and this is the ray. The normal would be pointing like this here, and we would find that the angle of incidence and the angle of reflection are the same. Okay, so this is a reflection. Has anybody got any comments about that code? I will put it on the website for you to download and have a read of. I'm lacking in it at the moment. If you were an optics engineer, what would you say to me? Would you give me $1 million for that code? Would you give me €10 for that code? Not bad, it works. How are you? You can, yeah, you can do that. You can just set the axis to make it look like a semicircle in words. Yeah. Make a nice circle, okay? Even aesthetic. So you wouldn't give me £1 million because it doesn't look nice. Okay. I like your. Can I do this? Axis. Do this from memory, so I think there's a command that hopefully works. There we go. So that new command I just put in, I told MATLAB to use -4 to -4 on the x-axis and -4 to +4. So -4 to +4 on both axes. So it's more realistic. Okay, would you give me €1 million now? What's lacking? What have we left out? Very good. Yeah. The reason this is only a partial solution is because in contrast to the flat plate example we had before, it was only a single reflection point. In this situation, there might be several points. that reflect. We have several reflects, certainly at least 2. Now our code only explicitly searches for 1. If we started off with an initial A and B in a process which worked from there, and we only found a single root, we would need to update this somehow to find other roots. That's pretty easy to do. I won't do it, but I'll give you guys the code and you can play with it yourself and see can you find other roots. Okay? Apart from that works. Okay? It's not the fastest in the world, and as you can see, it's not very clever because we would have started off with A is equal to here, B is equal to here, C was the midpoint. Our first midpoint was actually really close to the actual root. C was phi is equal to pi over 2, which is really close to where we want to be. But the next thing the midpoint algorithm does, it shoots C over here somewhere. So having been quite close to it, it then moved away. So it's kind of, not very clever. How do I know the solution is needed? Well, I don't. I know from experience that in these kind of optical problems, you do have more than one reflection point. But if I didn't know that, and if you were approaching this problem, you wouldn't know in advance. So it's a good question. What you would have to do is write a code that investigates that somehow, by maybe checking in the Newton. We'll look at the Newton-Raphson code now in a second, and we would write some Newton-Raphson code with maybe multiple inputs, multiple starting points, and each of those would maybe go to a different route and see how many routes we could find. That's a good question, which we haven't really covered in the notes. The first question is how many routes do you need to find? We're trying to find routes. Okay. Let's go back to our code very quickly, and let's have a look at the Newton-Raphson. Let's hope the Newton-Raphson that will work too. But everything else is the same. The preamble is the same. But this little bit here, if use Newton-Raphson equals 1, do this. Okay. So if you set the flag and tell MATLAB to use Newton-Raphson, this is what we do. We start off with an initial guess, x0. We'll make phi guess equals 0, so our initial point will be the rightmost point of the semicircle. We'll start there, phi guess equals 0. What do we do in Newton-Raphson? We work out the f value for that. So we feed that guess into our comp f value. Now we have a problem because in Newton-Raphson we need to get the first derivative. This is a complicated function. We don't know how to get the first derivative of it. The first derivative of an inverse cosine, it's a little bit tricky. So instead what we do is we use the formula I used in the notes, and instead we approximate the derivative by f at phi guess plus h plus a little step, minus the value at phi guess itself divided by this little increment. Okay, so this is the secant method. So this is not the Newton-Raphson method, this is the secant method. Okay. Very good. We set a counter running because we got to count just in case this thing goes on forever. We're going to just be able to know how many times we have run it. So we say while the absolute value of f value is greater than threshold and the counter isn't too large, we update. We say our next iteration is our previous iteration minus f divided by f dash. Okay, and we're using the finite difference for f dash. Then we update our value for f, we update our value for f dash, and we keep on doing it. So keep on doing it. A little bit of logic here. Anybody care to hazard a guess as to what these 6 lines of code do? So these 6 lines of code here, these 2 file statements. Anyone in Maynooth want to hazard a guess if you're still over there? Yeah, very good. So this Newton-Raphson method is going to give us values of phi. Now, we're only interested in the values of phi between 0 and pi, because they're the ones on the semicircle. Anything greater than pi, or less than 0, corresponds to the bottom half of the circle, which isn't there. We're only interested in on the top. So, but Newton-Raphson doesn't know that. Newton-Raphson could easily give us values greater than pi or less than 0, which are non-physical. Or it could wrap around. It could go to 2 pi or 4 pi or 6 pi. So any value outside our range, we have to pull back to within our range. Otherwise, we're searching non-physical space. We want to only search along the mirror, which is a semicircle. So that's what that little bit of logic is. And then we increment the counter. And then, so this will happen. This will keep on going and going and going until absolute F value is less than the threshold. And then at which point we found the root. We do that. Okay. So again, 5-6 lines of code. The hard part of this is putting all the stuff around it, the visualization, working out the equations, working out the function F. But the actual MATLAB code or the Newton-Raphson code itself, very straightforward. This time, let's use Newton-Raphson. Run the code again. Okay, and there we go. Much faster this time, you notice. And finds the root much faster. Same root as before, gives the same code as before. Okay, so good. Noticeably faster. A section took maybe half a second, and then this was pretty much instantaneous. Okay. Have any questions about any of that? What I'll do is I'll put that code, I'll comment it if I get a chance, and I shall put it on the website for you to download and have a read of. Okay. Laptop. Okay. Okay. Let's move on. Let's do another piece of code. Okay. Let's look at how to make a fractal. So I'm going to show you a bit of MATLAB code. I'll make this available too. It is not going to make the fractal that you need to make for assignment 1. It's going to make a different kind of thing. Okay, but it's going to show you how to do some things which may or may not be used. Okay? What? Okay, we're going to make what's called a Mandelbrot, after a French mathematician called Benoit Mandelbrot. You've all seen these. You know what they are. You've seen them. Students. Rats often have posters of this yoke. It's a very famous image. It's a fractal image. And I didn't make a handout. Maybe I should have made a handout to explain what it is. It's very simple. Maybe I should just run this first of all, and then I can explain what it looks like. Let's run it first of all, and then I'll explain it. That's probably the best way to do this. As well. Finish yourselves. Okay, just waiting for it here. It's that took a little bit long to run, so let me just reduce the resolution on it a little bit, okay? Minus. Okay. So that's the image that you've probably seen before. You see that NUIM, you can see that okay. Text me if you can't see it. So this is called a Mangrove set, and it's a fractal. Okay. So it's not the kind of fractal I want you guys to make, it's a different kind of fractal. But some things in common about how we make it. So let me explain what it is. First of all, it is a set up in the complex plane. So this is the complex plane, and here we have real values on this axis and imaginary values on this axis. And what we do is we discretize this region of the complex plane into lots and lots of little steps. So we sample all these complex points. Okay, so maybe I chose 200 points this way, I chose 200 points this way, giving 40,000 points in total. A lot of points. 40,000 points in total, sampling this region of the complex plane. For each of those complex points, we call it C. Okay, so C varies from minus 1.5 minus 1.5i down here, top right-hand side of the grid, which is C equals 1 plus 1i, and then all points in between. Now for each of these values C, we do the following. We start off at Z is equal to 0, 0, which is a point in the middle. Z is equal to 0, 0. And we do the transformation Z goes to Z squared plus C. We start off at 0, Z squared plus C jumps to there. We do it again. That point goes to Z squared plus C, so that'll go to C squared plus C, C squared plus C. It'll be another complex point. And then we do it again. We square and add C. 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 And this forms a sequence of points. And either one of two things happen. Either that sequence of points converges, stays bounded, okay, or alternatively shoots off towards infinity. Because if you imagine, if C is pretty big, Z squared plus C, so we start off at 0, go to C, then we go to C squared plus C, then we go to C squared plus C, and so on and so forth. If C is a large number, that's going to head off to infinity pretty quick. If C is a small number, it will stay bounded. It won't shoot off to infinity. So what we do is, for every possible value, we run this iteration many times, and we ask the question, does the sequence stay bounded? Does it stay a small number, or does it head off and become a really big number? If it heads off and becomes a really big number, we give the value 1. We assign the value 1 to this point C. If the sequence does not head off towards infinity, if it stays bounded, we give the value 0 to C. And we do this test for every value of C in this complex plane. And here what we see is the values of C out here all produce sequences that ultimately diverge. The values of C in here, not surprisingly, in and around 0, small values of C, produce sequences that do not head off to infinity. They stay bounded. They sort of rotate around and they stay finite. And the difference on the boundary between the two of them. Of all these little bits of detail, all these little islands and nodules and little bits of detail here. Okay, so this is a chaotic interface between the two. Okay. And what happens is, if you were to look at this in detail, we can zoom in on any region of this in more detail, and what we would see is just more and more and more detail. You can keep on zooming in, and this interface between where the sequence diverges and where the sequence converges never becomes simple. It's always chaotic. It's always potentially you can resolve it to greater and greater. Okay, let's run it again. Let's look at the code, and let's run it again. So I'll zip through this pretty quickly. I'm going to make this code available to you. Again, we clear, we close, we start. We decide for our picture, for our fractal, we're going to run this from real values going from -1.5 to 1, imaginary values from -1.5 to 1. Okay, we could zoom in part. In fact, let's do that. Let's zoom in. Let's go from, let's pick somewhere at random. Actually, no, let's not. Let's do that later. So we then decide we're going to sample along the real axis 200 times, -200, sample along the imaginary axis 200 times. So along the real axis is given by this, a step along the imaginary axis is given by this. So 200 by 200 gives us 40,000 points. So did that 40,000? Lot. We initialize for every value of C that we're going to step through. We're going to assume at the start that it does not go to infinity, it stays bounded. So we'll make them all 0 at the start. So values is a matrix, n by n matrix, full of zeros at the start. Okay. Threshold we'll see in a second. It's a threshold process and number of iterations. Now, this code actually, I got excited and I actually made a little animation where we not only make one Mandelbrot set, we can make 10 of them and make a little movie. But I've set that to only do one frame because it takes a while. If we're under 100 frames, you can see it's pretty slow. So we set the number of frames in our movie to 1. Okay. These values again, that's redundant, shouldn't do that. Start off, okay, I'll explain the power now in a second. What we do is we say, well, what frame counter are we doing? We're only going to do one frame counter here, one frame. And we say for the first frame, we're going to do the power is the power plus 1. Well, the power is defined to be 1 here. The power plus 1 will be 2. And what does that mean? Well, the sequence that we make is z goes to z squared plus c. And that will make a fractal image. We could also have a sequence whereby z goes to z cubed plus c, or z goes to z to the 4 plus c, or z to the z 5 plus c. So different values of this power will produce different sequences and different fractal shapes. Okay? So in this animation, we can run it many times, and each time we have a slightly different power, either z squared or z cubed or z to the 4, whatever. So we're only going to run one frame, so it'll just be z squared. Then we step through the real axis with counter 1. We step through the imaginary axis with counter 2. And we say the value c, remember the increment, so the iteration is z goes to z squared plus c, and we're investigating what happens for different values in c. So the first value of c we will try is when counter 1 is equal to 1, counter 2 is equal to 1. And that's given a lower real, that's imaginary, that's the imaginary part. And every time we go in here, we're going to increment ct and we're going to step along the real axis, keeping the imaginary part the same. That will step across the real axis, and then when we're finished that, we'll increment CT1, and that will increment the imaginary part by a little bit. So we're scanning along in lines along the real axis, okay, and then incrementing the imaginary, and slowly working our way through, scanning through this entire region of the complex plane. Again, I've initialized this for the third time. I initialize the value to 0. Number is equal to 0. Okay, well the number is this number in this sequence. We start off with the complex number 0, and then for the number of iterations we want to try, we go z goes to z to the power of the power, which is 2. So this is z squared plus c. Okay, and we're going to do that over and over again. And we asked the question, we started off with the number equals 0. We're going to do this many times. If at any point in this process the number is greater than the threshold, that would suggest that this sequence is becoming unbounded. It's getting very large. And we set the threshold. You can set it whatever you want to do. I set it equal to 10. So if this sequence ever produces a number greater than 10, it means it's growing quickly and it's not convergent. And in which case, we change the value in this matrix from 0 to 1 instead. Okay. So all the values were initialized to 0. We assumed that C would produce a sequence that did not diverge. But here we found that having run through the iteration Z goes to Z squared plus C a few times, we've produced a number which is very big, and therefore conclude that this value of C produces a sequence which diverges. And we note that we give it a value of 1 rather than 0. And we update. If that is the case, no point in keeping on going. We exit this for loop by putting the counter 3 equal to its final value plus 1, because otherwise you're just doing extraneous calculations. At this point, we've already discovered that the thing diverges, no need to run through sequence. Okay, and that's that. We end for counter 1 and counter 2. So at the end of this process, we have stepped through 40,000 different values of C. For each value of C, we've started off with Z is equal to 0, and we have done iteration Z goes to Z squared plus C many times. And we've kept track on when that iteration goes. In some cases, that iteration got very big, produced a number which was unbounded. To that, we gave associated with value C, we associated the number 1. And for other ones, it didn't grow unbounded, and leave it as a 0. So we end up with a matrix called values, which is full of zeros and 1s. And then we just plot it. We use what's called a surf command, which makes a nice 3D plot. You can do some nice shading and review it from above using this view to view it. And we can make it one, we can set the counter and we make a movement. Okay. People happy with that as a general idea? So this is similar to what you guys have to do for your problem. You guys have to discretize complex space, 40,000 different points. You've got to do a computation for each point. The computation you guys have to do is different from this. In your case, for every value of C, you've got to run the Newton-Raphson algorithm and see which of the 3 roots it finds. Here, run the sequence and see whether it converges or not. So that's where the codes differ. My code does something different from yours. But in both cases, we take the complex plane, we discretize it. For every value of C, we do some kind of test, and we produce an integer value. In this case, 0 and 1. In your case, either root 1, root 2, root 3. And then we make a plot, and the plot makes a nice plot. People happy with that as an idea? But note this will be available when you go and study it. Okay? Let me just do something, one other little thing you can do to make a nicer picture. Rather than producing zeros and 1s, we can do the following. We can say if we discover that the sequence diverges, rather than just putting in a 1 here, let us instead make note of how many iterations it took before it diverged. So rather than just putting in a 1, how many iterations did it last before it diverged? Because for some values of C, they diverge pretty much straight away. Other ones loop around for a while and then they diverge. So there's a lot of difference in where it diverges. Let's run the code again with that small change and see what happens. Okay, we get a slightly nicer picture this time. This time what we see is, again, these are all the points never diverge. The sequence stays the same. These blue guys here diverge pretty much quickly. But in and around the boundary, we see all these different colors. And the different colors, all these points do diverge, but they diverge at different rates. Some of them only diverge after maybe 100 iterations of this sequence, z goes to z squared plus c. Some of them diverge slower. Along the boundary, they diverge very slowly. They do diverge, but it takes a good while before that happens. With all these different little shapes and colors. Okay. So a nice thing you can do, I'll give this code to you. I won't, well, let's actually do it now, because I like this. It's Friday, do something nice. Let's do the code, then I'll let the French people go from, let's zoom in into this region here and see what it looks like, okay? So rather than going from -1.5 to 1, -1.5 to 1, let's go from -1 to -0.5 and 0 to 0.5. So zoom in this region here. And we can do that taking our code and just changing the limits here. We're going to go from -1 to upper is -0.5, and lower imaginary is now 0, and we'll go up as far as 0.5. So we're going to zoom in and part of the set. This should hopefully show the fractal nature. Okay, so this is now zooming in and part of it. Okay, see, you zoom in. On one scale, we had this big blobby kind of thing, but the zoom in, big blobby thing kind of reappears at a smaller scale. Plus all this color, where the points are, that the C is producing sequences which diverge but at different rates with all this beautiful color. If you were to zoom in, you could disappear down there. Honestly, you stick on some Pink Floyd, kick back, put on an animation, and people do this. People explore them. Mathematicians mostly, God love them, but they actually go and explore it, and they find places, and they give them names. Because it looks like a map of the world. It looks like a map of Middle Earth kind of stuff, you know. And you can go and explore it, and you can go and find interesting shapes and interesting regions and interesting little artifacts. So people do go and explore this. They write codes to go and find out interesting parts of the Mandela because it never repeats. It almost repeats. It has variety at different levels, but there's always new structure emerging and stuff. So you can write this code to go and explore. Imagine a little spaceship, and you're sort of just, you know, zooming into the different regions and exploring. And people do this. Okay. Okay, so I'll make this code available to you. Let's take a break until 4 o'clock. That allows the French people to go. We'll kick off at 4 o'clock and we'll start a new handout, okay? Good for you over there, that's great. And so, let's start a new section. New section. I'm keen to give you all enough information so you can do the assignments. So hence I'm jumping around a bit. So we're going to go to handout number 3, and hopefully next hour I can tell you enough so you can make an intelligent stab at that part of your assignment that requires numerical integration. So numerical integration is the evaluation of a definite integral of the form integral f of x between a and b. Okay, done numerically. F is called the integrand, and a and b are the lower and upper boundaries. Straightforward stuff, you all know this. You all know how to integrate, so it can be worked out exactly provided that you have knowledge of what is called the antiderivative of f. So the antiderivative. What is the antiderivative? Well, the antiderivative is that function such that when you differentiate it, you get f back again. So in that case, we would have, here's our definite integral we would like to compute. And we know that the integral of f is given by capital F because the derivative of big F is little f. And then we just work out big F at the limits, b and a. So fb minus f of a. So some examples, when you know all this, this is just purely just to set the scene so we know we're all on the same page. Compute the integral I is the integral of e to the minus 5x between 0 and 10. Okay. So this is what we have. We know that e to the minus 5x is in turn the derivative of this thing here, because when we differentiate this thing, we get minus times minus 5 divided by 5, all of which cancels out to 1 times e to the minus 5x. So this here is the antiderivative of this. And the integral of the derivative of something is just equal to something itself. So we get this thing here in brackets minus e to the minus 5x over 5 evaluated at the limits. It is evaluated at 10 and evaluated at 0. And we get, we can flip the limits, go to the minus, we get 1 over 5, 1 minus e to the minus 5 times 10, or 1 minus e to the minus 50. Very straightforward. However, in many applications, we can't do this. So again, the similar pattern emerging here in all our lectures is that you've learned a whole bunch of stuff in school and in college, but in actual fact, when you want to go and do practical work, you run up against problems because we do this stuff analytically. We have to do it approximately in some way. So reasons we can't do it exactly is because the integrand is too complicated and we simply do not know what the antiderivative is, this function such that we differentiate it to get little f. Or it's an empirical function. You don't even know what the function is. All you have are sample values of it. When you have sample values of it, how do you integrate it? Okay. So we have to use numerical. How do they work? Well, here's this. So for example, on the picture on the right here is a funny looking picture. What's happening is we have a sphere, two-dimensional sphere, so a cylinder really, in 2 dimensions, made of some kind of material, some kind of dielectric material. There's a plane wave traveling from left to right over here, and the plane wave hits this cylinder and scatters. So by scatters, I mean some of it reflects back from the direction it was coming. Some of it maybe reflects out in these other directions over here, above and beyond. Some of it diffracts around the top of the cylinder and emerges around the back. Some of it penetrates through the cylinder, bounces around inside the cylinder many times before emanating from the back. And what you get is you had a nice simple plane wave arriving in. You have all these complicated waves that are bouncing around in different directions, and you get what's called an interference pattern. So all these nice colors here, the yellows and the blues and the reds, are peaks and nulls, where you have an interference between a wave traveling from left to right and a scattered wave traveling broadly from right to left, back again. So these are useful things to make, nice things to pretty things to look at, but very useful in electromagnetics because you'd be trying to work out scattering for maybe radar purposes, etc. Trying to work out what happens when a strikes from reason. So my students wrestle with this, and part of making a nice picture like this involves an integral, such as this, the details of which aren't hugely important to us, but suffice to say it's an integral over a straight line from limits minus delta over 2 to plus delta over 2 times this. And what does this mean? Well, what the student does is he takes the cylinder and he breaks it up into little chunks. So on the surface of the cylinder, he breaks it up into many small little discretizations. And then he makes a big matrix, and the big matrix contains the interaction between all the different little discretizations. So this thing here, this integral on the left-hand side, is computing the interaction between one such little discretization and another such little discretization. And if you can work out all these little interactions, put it all together, and make a nice picture of it. But the problem is, how do you make this integral? This interaction between one little discretization and another little discretization requires we do an integral like this, of this function here. This is called a Hankel function. It's a function which models wave behavior in 2 dimensions. Know about it. This here, J, is the surface current in that little discretization. So it's a measure of the surface electric field, basically, measure of the surface magnetic field. Again, the details aren't important. What is important is to know that in order to work out the interaction between 2 points from here and here, we need to be able to do this calculation, this computation. And we can't. We can't do this analytically. We don't know the antiderivative. Here's another example. Someone gives you outputs and data from a experiment to have an inductor, and they measure the voltage across the inductor at discrete sampled time. Okay, discrete sample time, and they ask you, well, what is the current flowing through the inductor? And the current flowing through an inductor is related to the voltage in this fashion. V is equal to L times the I dt. So inverting that, we'll get I is equal to 1 over L times the integral of the voltage. And the problem is we don't know what the voltage is. We don't know, we haven't got a functional form of it. We don't know is it a sine function, is it an exponential function, what kind of function it is. All we have are values of it at discrete moments in time. So we know there is some underlying function. There obviously is. We just don't know what it is. All we've got information about it at sampled units of time. And we would like to be able to integrate this nonetheless. So how can we integrate it if we don't know what it is? And again, we can use numerical integration. So all forms of numerical integration really rely on this slide here. This slide here is very important. It tells us that this integration process of integrating a function f of x between a and b is a formal mathematical process you can do. You find the antiderivative and you get a number. But more intuitively, what it actually means, what you're actually doing when you get that number, what that number actually represents is this area in red. So here's the function, this kind of purple curve. Here's the x-axis. Here is b and a on the x-axis. And when you integrate f of x between a and b, you get a number. And what that number is the area of this red curve. That's just a fact. You're not going to get that. You can do an example. It's, let's integrate 5x between 2 and 6. So this is a simple linear polynomial, linear function. Going to integrate it between 2 and 6. So what do we get? We get 5x squared over 2, evaluated at 6, evaluated at 2, and get the difference. And that works out as 5 times 36 over 2 minus 5 times 4 over 2, which is 90 minus 10, which is 80. So this is a number. You do a definite integral of this number. So how do we interpret this number? Well, we interpret this number as follows. This black line here is the function f of x equals 5x. It passes through 0, 0, 2, 10, 6, 30, and other points in between. And we're being asked to integrate it from 2 to 6. So between 2 and 6, this black line, this curve, contains or traps this area here in blue. And this area in blue is made up of a rectangle, and then sitting on top of the rectangle is a triangle, or a trapezium. I'll be pedantic about it. So the total area between the black curve and the x-axis is the area of the triangle and the area of the rectangle. The area of the rectangle, well, the base is 4, between 6 and 2. The height is equal to the function value at 2, which is 5 times 2 or 10. So this height is 10, width is 4, that's 40. The triangle, its area is, well, its height is the difference between here, which is 10, and the function value at 6, which is 30. So the difference between 10 and 30 is 20. So the triangle has height 20, and it also has base 4, and it has area, therefore, 20 by 4 divided by 2, which is also 40. Add 40 and 40 together, you get 80, okay, which is what we need to do. So that's just a little check. For that particular case, the area under the curve happens to be the same as the definition. Now I've only shown it for one, that's not a proof, but you can go and try it for other things as well, and it always works out. And not only for straight lines, it works out for any function. So this is the key to numerically integrating functions, because if we have the function and we want to numerically integrate it, that is equivalent to numerically estimating this. And if we can estimate this area, it's the same as numerically estimating the integral. So all these methods do something very simple to try and guess what this area is. There's several ways of doing that. And that's how they differ. Okay. So some of the rules we'll be using are the midpoint or rectangular rule, the trapezoidal rule, Simpson's rule, and the Euler-Maclaurin formula. So let's work our way through these. They are corresponding more complex as you work your way through them, and they're correspondingly more accurate as you work your way through them. So let's see why that is. And before we do that, a quick word. numerical integration is often called quadrature. It's an old-fashioned word you'll come across. And the term quadrature originally meant the process of finding a square with the same area as the area enclosed by an arbitrary curve. So they would try and estimate the area enclosed by a curve by finding a square or a rectangle generally with the same area as the curve, or what's inside the curve. And they do that for various. So the midpoint rule is the simplest thing you can possibly do. You take the interval of interest, a to b, which is where we're integrating along, and we divide it into n equal strips or width h, where h is given by the interval length divided by n. Straightforward. And then we make some little nodes which are at the center of each of these little strips. xj is at the center of the jth strip. So specifically, xj is given by I plus j minus a half times h for all n strips. And also, we work out function value. We're trying to integrate the function f. We work out f at the center of all these strips to give us f evaluated at xj, which we refer to as f sub j, just to make our notation a little bit simpler. So f sub j just means the function f evaluated at x sub j, and x sub j are the center of these strips. So there's our picture. There's a function we're trying to integrate. There's a, there's b. We make n equal strips along here. x1 is the center of the first strip, and f applied to x1 gives us f1. F applied to x2 gives us f2. F applied to xn gives fn, and so on. Okay, that's our picture. It's very straightforward. So what do we do? It's pretty obvious what we do. We're trying to estimate the area between this curve and a and b, and we have approximated this area by n rectangles. So the area, the sum of the area of these n rectangles is approximately equal to the area under the curve. So we can approximate the area by adding the n rectangles. So this is the integral we want to do. This is the area of n rectangles. So for each rectangle, the area is just the width, which is h, multiplied by the height, which is fj, for the jth rectangle. Okay? Very straightforward. You add all those together. This is the area of the jth rectangle. It's the width by the height. You add them all together for all n strips. This gives you the area, the sum of the area of all the lines. And that should be similar to this. And you can write that. You can take the h outside and write it as that. The question, why that last step, taking the h outside, why is that useful if you were to implement this numerically on MATLAB or on a processor? Why would you do it this way rather than this way? They're identical. Yeah, exactly. That's the answer. It's it'd save time. In the first one here, we'd multiply all the nh. That's n multiplications, and then on top of that, n additions to add them all up. Here we just do n additions and a single multiplication at the end. So you've saved yourself a lot of computation. The little tricks like that are very useful when you're doing this kind of stuff. As well as making stuff accurate, you've got to think about how to make it run efficiently. Okay? Because if you're trying to do this in a games console or something, you want it to be as fast as possible. Okay. So, very straightforward to do. And again, similar process to what we did before. The actual algorithm is really simple, very simple. The hard part is trying to figure out how good it is and trying to work out, is this a good method to use and trying to characterize how good it is. So let's do a bit of error analysis. Let's say that the integral that we want is equal to this midpoint sum plus some error. We call it epsilon r, or the rectangular rule, epsilon r. And we can estimate epsilon r as follows. We know epsilon r, the error inherent in doing this, will be bounded. It's going to be bounded by, it's going to be smaller than or equal to h squared. So the smaller we make h, the better. Makes sense. Multiplied by b minus a, which is the total width of the interval, divided by 24. We'll see where 24 comes from. Multiplied by m, or is the maximum magnitude that the second derivative of f takes between a and b. This error, this is a bound on the error, so is going to give us the right answer plus this error, and this error is guaranteed to be less than this. It's not obvious at all where this comes from. Let's try and work out where this might come from. So where does that term come from? Can we work it out? Well, let's try and see where it might come from. We saw the Taylor expansion before, and we said that f of x can be written as f of a plus all these correction terms, and they normally go off to infinity. If instead you only take a kth degree polynomial, so you take terms up as far as the kth derivative of f and terms of x minus a to the power of k, say you truncate it at that point, it is possible to write a remainder term for what's left over. Okay, so this is an estimate, and what's left over is given by this, and it's possible to show, but the remainder term is given by a term very similar to all these other terms. It's a k plus first derivative of f divided by k plus 1 factorial multiplied by x minus a to the power k plus 1, so very similar to all these terms, but the derivative is not at a, it's at some value eta, where eta is some unknown number between x and a. This is the problem. We don't know. This remainder term would be really great if we knew what this was, because then we could put it in and we could make this exact. But the problem is we don't know what eta is. It's value between x and a. Some value eta exists such that this remainder is given by this. Okay. That's not nice to see that. It's possible to show that using what's called the mean value theorem. So last Tuesday, or Tuesday week, we saw something called the intermediate value theorem, and we were looking at the bisection rule. We didn't prove it. So the mean value theorem is, again, one of these mathematical theorems from pure maths, which enables us to say things like this. So you can look it up on the book if you wish. By the way, books. People have been asking me about books. Let me just say now, because I've been meaning to say, I recommend a few books for this course. For example, Stroud, Kenneth Stroud. I'll write this so that anyone people can hear it. Advanced Engineering Mathematics. And also Kreutzig, I think is how you spell it, Kreutzig, Advanced Engineering Mathematics. That's Stroud, S-T-R-O-U-D, and Kreutzig, A-R-E-Y-S-Z-I-G. Erwin Kreutzig, I think his name is. Both of which are called Advanced Engineering Maths. Different books, but same title, okay? So these are books I would suggest people, if you're interested in reading more about this stuff. It covers quite a lot of what we cover in the course. I don't know between them if they cover everything, but they cover quite a bit. And they probably cover other stuff as well. So they're useful books to have in general, I would suggest. They're just good engineering maths books. So, second name is Kreutzig, K-R-E-Y-S-Z-I-G. I think his first name is Erwin, maybe, E-R-W-I-N. Pretty famous book. There should be copies down the line. Advanced Engineering Mathematics. So you can read about, covered the mean value theorem, I don't know, but you can read about the value theorem on the web otherwise. We don't need it. We're not going to use it, but suffice to say, this is how it is. So let's imagine we're trying to work out how well this rectangular rule works for us. Okay, so let's take a single rectangular strip, and rather than doing all n strips, let's just focus on one strip and see how well we can do the integration over one strip. Let's assume the strip goes from 0 to h, and the midpoint therefore is h over 2. Okay, h over 2. So we would like to do the integral over this strip from 0 to h of fx, and the midpoint rule says that it is approximately equal to value at the midpoint multiplied by h, and we'd like to work out how good an approximation that is. Well, within this region, from 0 to h, we can get f of x is equal to, using a Taylor series, f of h over 2 plus a linear correction, x minus h over 2 times the first derivative, plus this remainder term, x minus h over 2 squared, f double dash evaluated at eta, for some eta in this interval. We don't know what eta is, some value in there, we don't know what it is. Well, integrating f of x from 0 to h, therefore, is the same as integrating what's on the right-hand side. We integrate the first term, will just give us h this, because there's no x here, this is just a constant. This here, when you integrate it, goes to 0 because this is a constant, and for half the interval, from 0 to h over 2, this will be negative. From h over 2 to h, this will be positive, and it cancels out. So this all goes to 0. The second term goes to 0, and we're left with the third term. So the first term gives us h times this. Second term goes to 0. The third term, when you integrate it, you get f double dash eta over 2 factorial. And when you integrate x minus h over 2 squared, evaluate it in this region, you get h cubed over 12. You can prove that for yourself. Okay? So this becomes this. So what we've shown using our mean value theorem is that the actual number we want to get for this little interval is equal to what the rectangular rule gives us, plus h cubed over 24 times the second derivative evaluated at some value eta. We don't know what that value is. So this is the error in a single strip. The overall error over n strips from A to B, therefore, is we just sum this n times. For each strip has this little eta term within it, where this maximum occurs, or the remainder term works. And we get this. All we can say is each of these little second derivative terms are smaller than MR. Remember MR, we introduced it, it's the maximum of the second derivative in the interval A to B. So we can say that this is less than or equal to this because all of these second derivatives is less than MR, because MR is defined to be the maximum of the second derivative in that region, times h 24, which is equal to, well, there's no j's anymore, we've got rid of all the j's, so there's just n terms here, so we just get an n times this. And n is equal to b minus a over h, so we can get b minus a over h, and this becomes h squared. And this is the result we had a few slides ago. Okay, so this is our error analysis. It's important to know when you're applying the midpoint rule, it's good to know how to do it, but it's also good to know how accurate it's going to be. And we can see that the error in the midpoint rule is going to be something like this. So it's going to be about h squared, of the order h squared. So in other words, the smaller you make h, the more accurate it's going to be. What's the problem with that? If you make h smaller, what's going to happen? We're doing this on a computer. Notice yourself, only 20 minutes to go, you're almost there. Let's look at the picture. To make h smaller, what's the problem? You get more of these little divisions, you get more work to do. This integral, this approximation you're doing, you got to do a summation, and that takes time on your computer to do. So the more of these divisions, the smaller you make h, the larger you have to make n. The larger you have to make n, the more work your computer has to do, and the slower this becomes. So we can make this error go away, turn to our error analysis. We can make this error go away. Where's it gone? It is. We can make it go away by making h really small. However, making h really small will then take a long time to run on your computer, and also there's an issue with round-off error. We make h very small. Computers can only store numbers to a certain, and the more numbers you got to add together, the more round-off you're going to get, and you actually start losing accuracy. So we have to find a better way of beating this rather than just making h small. But before we do that, let's do an example. Let's use the midpoint rule formula to calculate this function, or this integral. Now we wouldn't do this numerically normally because we don't need to. We know the answer. It's x to the 5 over 5 evaluated at the limit. So the answer is 0.2. So we know this. So this is purely for illustration because we know the answer. And let's try it with different h sizes, making h smaller by a half every time. And every time we do this, let's compute epsilon r over h divided by h squared, because we expect the error to be proportional to h squared. According to this error analysis, it's h squared multiplied by some stuff. If we work out the numerical estimate, compare it to 0.2, get the error, divide it by h squared, we should see a constant emerging because the error should be proportional to that. So that's what we did. Actually, sorry, I do something slightly different in the solution. I don't use these h's. I actually use these h's. So, it's the same idea. So as h gets smaller, the amount of work, so h gets smaller by 10 every time here, which means the amount of work your computer has to do grows by 10 every time. There's 10 times the amount of work summations you have to do. Well, here's the interval. Starts off pretty close to 0.2, gets closer, 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 and by this stage, we're here. And what we can do is we can see the error is equal to 0.2 minus this. We divide it by h squared, and we see error divided by h squared is pretty much constant, confirming our suspicion. Our error analysis tells us that the error is equal to h squared times some constant. Okay? And in this case, the constant would seem to be 0.16666, blah. Okay? So this verifies our error analysis. It suggests our error analysis is correct. So another way of framing this error analysis, well, if the error is proportional to h squared, it means error is equal to alpha times h squared. It means if we were to do this on a log scale, log of the error will be log of alpha times h squared, with alpha plus log of h squared, which is log of alpha plus 2 log of h. Let's put this data onto a log plot. Let's work it out on a log plot first of all. Here we had h getting smaller by 10 every time, 0.1, 0.01, 0.001 all the way down. So let's plot log of 10 will be minus 1, minus 2, minus 3. And let's plot log of epsilon r minus 2 log 10h. And according to our little error analysis here, log 10 of epsilon r minus this should be a constant. It should be log 10 of alpha, where alpha is equal to 0.166. And lo and behold, yes, we get that. We get the difference between the error and h squared on the log scale should be a constant offset, 0.77. We see that in the picture. This is a very important picture. So let's take a minute and understand it. What I've done here, I've taken this problem and I've plotted h on the x-axis on a log scale, the different values of h. So here's log 10 of h equals minus 1. This is h is equal to 0.1. Here is log 10 of h is equal to minus 2. So this corresponds to h is equal to 0.01. Here is h is equal to 0.001, corresponding to minus 3 on the x-axis. Minus 4 here means log 10 is minus 4, or 10 is 0.000. So this is h getting progressively smaller on a log scale. H is getting 10 times smaller between minus 1 and minus 2, between minus 2 and minus 3. On the y-axis, I have plotted the log of the error, and that's in blue, the straight line curve case. So the smaller h gets, you can see the smaller the error gets. As h gets smaller, the error falls and falls and falls in this straight line fashion. Okay? And what we would expect if our error analysis is correct, our error analysis suggested that epsilon r is proportional to h squared. That means on a log plot, this should have the same shape as log of h squared, which is the red curve, just offset by a constant amount. The constant amount being about 0.777. And we see this is the case. As h gets smaller, our error gets smaller and smaller and smaller, and it goes in a way according to our error analysis. As h gets 10 times smaller, it scales just like h squared. It's always equal to h squared minus some offset. So people happy with this graph? Log graph is useful because if we try to do this information, these errors are very small. If we try to plot the error on a linear graph, what you'd find is it's so close to 0 you wouldn't be able to see anything. So by using a log graph, we can separate it all out and we can see this more explicitly. Okay? So here are h values on the log scale on the x-axis. On the y-axis, we have the y-axis we have error values on a log scale. And we see that the error evolution follows log of h squared. That's important. We're going to come up with something like this in a while. So we need to familiarize ourselves with this so we can recognize when something is better than this, which will be in a few slides time. So the midpoint rule is exact when you apply it to integration of constant functions. If you use the midpoint rule to work out the integral of fx equals constant, it's going to be exactly right because it's going to work out the area exactly correctly, as you'd imagine. What's slightly more surprising is that you can use the midpoint rule. The midpoint approximates the function locally as a constant, but surprisingly, you can use it to integrate linear functions exactly, even though it's approximating as locally being constant over these little strips. So I'll leave an exercise for yourself to verify that is the case, that the midpoint rule will exactly integrate a linear function, and try and work out why that is. Why is that the case? Now, trapezoidal rule, I'll do this very quickly because it's a flow. The trapezoidal rule, well, how can you do a better estimate for the numerical integration? Well, what you can do is the following. You can take the area, the red area we're trying to estimate, and rather than estimating it as a sequence of rectangular strips, you try and estimate it as a sequence of trapezoids. And a trapezoid is a rectangle with a little triangle at the top. So what we do is, again, we make n equal strips, slightly different this time. We have xj not being the midpoints, we have xj being the starting points, only slight difference. Fj is still the value of the functions at these nodes, such that f of 0 is f of a and f of n is equal to f of b. So let's draw a picture. So here's for the trapezoidal rule, slightly different. X0 corresponds to a, xn corresponds to b, and these nodes are now at the start of the intervals rather than the midpoint. Here's f0, the function value at x0, and so on and so forth. So we want to approximate the area in one of these little strips. Previously, we approximated it as a rectangle. Let's see, can we do something better? So what we do is, we'll approximate it as a trapezoid, and then we can sum up all these trapezoids, the area of all these trapezoids, to get now it turns out that the area of a trapezoid on the interval xj, xj+1, so rather from j minus 1 to j, the area of the trapezoid is given in a second. So you can add all these all up, and when you add them all up, what you get is, well, for j is equal to 1, he's going to appear twice. J is equal to 2 will appear twice. So we'll have j over 2. All the interior nodes appear twice. You get h times all the interior nodes. So by the interior nodes, I mean the ones not on the boundary. So x1, x2, x3, all the interior ones. The two guys at the outside, x0 and xn, they only appear in the first and last trapezoid for h over 2. So that'll make more sense in a second. Let's look at the area in one of these little strips. So here is the area in trapezoid j. So we have xj to xj+1. And what we do is we estimate the area under the curve by a rectangle, which is in red, and a triangle, which is in green. The area of the rectangle is the width, which is h, multiplied by x, or fj, which is the height. That's the area of the triangle. Well, the height of the triangle is f of j+1 minus f of j. That's the height of the triangle. We multiply it by half the base, h over 2. That gives us the area of the triangle. Add these two together, you end up getting h over 2, f of j+1 plus f of j. You can work out the details yourself. So this is where this expression here comes from. And what we find is, for all the interior nodes, f of j+1 gets counted by a factor of h over 2 as part of this trapezoid and also the neighboring trapezoid. So it gets counted twice, so the 2 disappears. Hence, the h multiplying all these interior nodes. The nodes at the end only get counted in the first trapezoid and the last trapezoid. They only appear once, so they retain the h over 2. That's why in this expression, some of them are h over 2, some of them are h. The end ones are h over 2, the interior ones are h, because they get counted twice. They contribute to two neighboring trapezoids. Okay, the error involved is error trapezoid. This is the actual integral. This is our estimate. The error is given by that. I won't do the details. You can show that an estimate is given by this. It's the same as the rectangular rule, where m is this maximum of the second derivative. Interestingly, it's worse than the rectangular rule. The rectangular rule was h squared over 24, which is smaller. This is h squared over 12. So curiously, this actually gives us, on average, a slightly worse, or pretty much the same kind of behavior as the rectangular rule. It doesn't give us any better behavior. The error is still h squared. It still goes as h squared. So the way you make this smaller is by making h smaller, but the error only goes down with h squared. I can do an example, the same example as before, integrating x to the power of 4. The red line here is log of h squared on a log scale. The blue line is the midpoint rule, as we saw before. Its behavior mimics h squared, which suggests that the error behavior is exactly of order h squared. And it means the error is proportional to h squared, because on a log scale it's separated by a constant gap. And the trapezoidal rule is in black, and again it too has an error proportional to h squared, because on a log scale it differs from h squared just by a constant amount. So it hasn't improved very much. It's still, you've got to make h smaller in order to make it better, and it only gets smaller. The error only drops as h squared. So you've got to make h smaller. So let's do one more rule and then I'll let you go because I know you're tired, but just in order to round this off and see how you can do something better. We went from a constant, piecewise constant approximation to a kind of a linear approximation which produced a trapezoid. Didn't do us any good. Our integration rule wasn't any better. So let's try and do something a little bit better and see if it works. Rather than using a trapezoid, which is a piecewise linear approximation, let's use a piecewise quadratic approximation. So to derive this, same as before, with n strips, and xj are the start of the strips as before. Now, what we do is we take two strips together. Okay, so for example, the strip involves the nodes x0, x1. The second strip is from x1 to x2. Let's combine those two strips together and consider the interval from x0 to x2. And what we're going to try and do is make a quadratic polynomial that passes through the points x0, f0, x1, f1, and x2, f2. From the previous case, we made a linear polynomial that passed through x0, f0, and x1, f1. That was the trapezoid rule. Here, now we're going to make a quadratic, a parabola, that will pass through this point and this point and this point. So here's the picture. We have strip number 1, strip number 2. In the trapezoidal rule, we just made a straight line from f0 to f1, which meant locally we were approximating this curve as a straight line. Here instead we make a curve which goes through f0, f1 and f2. And this curve should be able to better fit the underlying curve, the underlying curve. So you can fit things better with a curve than with a straight line. Okay. I'm going to skip these. We'll do this on Tuesday. This is just some detail as to how you make this quadratic approximation, because I'm keen to get to the net result of all this to show you that it's better. Okay? So suffice to say, we'll do the details of this on Tuesday. It is possible to work out an equation for a polynomial that passes through these points. And we'll see the details on Tuesday, how to do that. Okay. Skip through all this, pretty straightforward stuff. All this on Tuesday. It's exciting, isn't it? So do all this, and then what we can do is we can integrate that polynomial exactly. It's a quadratic polynomial. We know how to integrate quadratic polynomials exactly, and we get this as our estimate for the area in, here it is. Here's our estimate for the area under the curve in those first two strips. H over 3 times f2 plus 4f1 plus f0. So we'll do the details of this on Tuesday, but suffice to say, this is an estimate for the area under the curve for the first two strips. For the second two strips, we get this, and so on and so forth. And you can add them all together, and we get Simpson's rule. We say that the area under the curve is approximately h over 3, the function value at the first node, plus 4 times the function value at the second node, plus 2 times the function value at the third node. Sorry, I should say that again. Sorry. H over 3 times the function value at x0 plus 4 times the function value at x1 plus 2 times the function value at x2 plus 4 times the function value at x3. So it alternates 4, 2, 4, 2, 4, 2 until we get to the very end, it becomes 1. So this sum you can do, it's very easy. You just recognize the odd nodes and the even nodes. The odd nodes get multiplied by 4, the even nodes get multiplied by 2, except the 2 end nodes which get multiplied only by 1. So this is going to give us a better estimate. And you know that the error is given by this. It's a similar looking expression to what we had before. But notice, rather than being h squared, the error is now h to the 4. That means for a given small value of h, the error is less than h to the 4. So if h is small, h to the 4 is really small. For the other two methods, we had h was the step size, the error was h squared, which is pretty small. Here, for a similar amount of work, not a huge amount more work, n computations, just with different coefficients, we get an error which is h to the 4, which is going to be 2 orders of magnitude better. So we expect, therefore, that on a log scale, the error is going to look not like log of h to h squared, it's going to look like log of h to the 4. So here we go. Here's the graph I wanted to show you. Same example as before. It's integrating x to the 4 from 0 to 1. Here is log of h squared in red, and here is the midpoint rule and the trapezoidal rule. As h gets smaller, these errors get smaller, but 10 to the minus 8, 10 to the minus 10, so 8 decimal places, 10 decimal places accuracy. But with the Simpson's rule is in yellow. And the Simpson's rule, you can't really see it very well, but it's in yellow there, it's in your notes, is tracking this light blue curve. This light blue curve is h to the 4 on a log scale. It gets smaller much more rapidly. As h gets smaller, it gets much smaller, much more rapidly. And you see the Simpson's rule for using smaller and smaller h's, the error drops much more rapidly. So let's make that explicit. With a value of h equal to 0.01, which is minus 2 on this x-axis, the trapezoidal rule and the rectangular rule will give us an error of about 10 to the minus 4, which is 0.0001, 4 decimal places. Using the Simpson's rule will give us an error of about 10 to the minus 10. It's 10 decimal places rapid. But using a similar amount of effort on your computer, just n computations pretty much, just multiplications and additions. It's so much better accuracy. So we'll leave it there. On Tuesday we'll go back and look at Simpsons and see where those coefficients come from. But this is what I wanted to show you. Okay, we'll leave it there. Thank you, Manus. Thanks for hanging in there for a long session. Hope everything was okay. I shall see you on Tuesday. There'll be a recording of this available to as soon as I can get it up. Okay? Take it easy. See you soon. Bye-bye. Cheers, guys. Okay. See you again later. Yeah, that's what I'm going. Yeah, no worries. Yeah, just, you know, for the play clips, which one? Like the random numbers? Yeah, like random. Yeah, I'm not sure as well. Okay. Yeah. And you know when you say in the question, randomly, uniformly clear 3D things. What do you mean by that? Uniformly. Well, our random number generator that we can trust 10. So minus 1 plus 1. If you make a random number generator according to the rules we gave, it's going to give, and you can scale the number so that lambda minus 1 just 1. It's going to be uniformly distributed, by which I mean the real values will be